So my name is K. Veeraswamy, Senior Lecturer in Electrical Electron Engineering, Government Polytechnic, Nirmal. I am teaching 5th semester subject AC Motors, subject code 18E502C. The main topic, 3-phase induction motor. Subtopic, speed control of 3-phase induction motor. In the last class, so first we will recap previous class. So we have discussed various types of speed control, right? That is the stator side and rotor side. In case of a stator side, we have by changing the supply voltage, by changing the supply frequency, by changing the number of stator poles, right? These are 3 methods from stator side. Similarly, from rotor side, rotor rheostat control method, by injecting the EMF in the rotor circuit, and third one is by cascade connection, simply by cascade connection. Speed controls. In the last class we discussed first two, that is by changing the supply voltage, and second one is by changing the supply frequency. We know that 3-phase induction motor is practically a constant speed motor, more or less like a DC shunt motor. The speed variation of a DC shunt motor is possible within the wide range with good efficiency, merely simply by maintaining some field rheostat. At the same time, a 3-phase induction motor is not possible. Why? Because we have to lose efficiency, and again we get very small variation in the speed control, right? So in that first two, one is by changing the supply voltage and by changing the supply frequency. We know that torque is proportional to slip S and square of the voltage V. Suppose if you decrease supply voltage, then what happens? When supply voltage decreases, to maintain a constant torque, V square. When V decreases, to maintain a torque constant, S must increase. When S increases, what happens? Speed decreases, right? So in this way we can change the speed of the 3-phase induction motor simply by changing the supply voltage, but very large change in supply voltage causes very small in speed variation. That's why it is rarely used. It is this method rarely used. And next one is by changing the supply frequency. So we know that synchronous speed Ns is equal to 120 F by P, and rotor speed Nr is equal to 1 minus S into Ns. That is equal, rotor speed is equal 1 minus S into 120 into F by P. So that means rotor speed is directly proportional to frequency and inversely proportional to number of poles, right? frequency. Here P are constant, P constant, so frequency. But simply by changing the supply frequency, speed can be controlled. Right? That means when flux increases, what happens? When flux increases, speed increases. Speed increases. Right? But this method has some limited applications. That means by changing the speed of the generator or prime mover, then automatically supply frequency changes. Supply frequency can be increased, but more variation in supply frequency can be achieved by simply by using a semiconductor device. That means first change a DC voltages, AC voltage into DC voltage. By using a inverter circuit, we will convert DC voltage into AC. Controllable voltage and frequency. Controllable voltage and frequency. Right? So we can control voltage and frequency by changing the pulses to the thyristor circuit. Pulses to the thyristor circuit. And in this case, merely changing the frequency may cause saturation of the pole, saturation of the magnetic field. Our air gap flux is saturated. Why? Because the induced EMF in the stator circuit or rotor circuit, right, it depends upon flux into frequency. Flux into frequency. E is proportional to flux into frequency. Suppose flux increases or flux decreases, automatically induced EMF decreases, right? To maintain a constant voltage, we increase the flux. It increase the flux. Or if V is a constant, when flux decreases, frequency decreases, automatically first increases. When frequency decreases, flux increases. Flux increases, right? To avoid this, so we have to change voltage and frequency also. Voltage and frequency. So that is a very important method, V by F method, V by F control method. We have to control frequency and voltage, right? Both frequency and voltage, not only frequency. So therefore, if we maintain a constant ratio, V by F ratio constant, then automatically flux remains constant. When flux remains constant, that means there is no variation in the saturation of the air gap flux. So we can easily achieve the desired speed in most of the industries. So using this V by F control method, voltage and frequency control method, right? And next today, so we will discuss third method in the stator side, that is by changing the number of poles. By changing the number of poles, by changing the stator number of poles, we can get variable speeds. Variable speed, right? So today topics, third method, speed variation by changing the stator poles. So it is the third method from stator side. Last method from stator side, right? Next, if you observe this slide, Ns is equal to 1 minus S into F by P. From the above equation, it is also clear the number of pulses. By changing the number of pulses, this change of pulse is achieved by the following two methods, right? The following two methods. One is by two separate windings on stator, and second one is by changing consequent pole technique method. Consequent pole technique method. Consequent pole technique method. Clear? Speed of induction motor NR is equal to ns times of 1 minus s times of ns, that is 120 F by P. So if you change the number of poles, automatically speed changes, right? So there are two methods are there. So one is by using two separate windings on stator, or by consequent pole technique method. So let us consider first one, that is by using two separate windings on stator. So in this method, the stator is wound for two independent windings for different number of poles, say 4 poles and 6 poles, right? It is designed for or wound for two different poles. One is slip is equal to s is equal to 0.03, then rotor speed is equal 1455 rpm. Suppose it is wound for 6 pole, so it becomes 1 minus 0.33 into 120 into 50 by 6, that is equal to 970 rpm. Right? Here we assumed that slip is equal to 3% and frequency is equal to 50 Hz. Right? So from this we can conclude that by changing the number of poles, we can change the speed. So in the first method, the motor is designed for two separate windings, and one winding for 2 poles, another winding for 6 poles. The two windings are to be insulated from each other. When any one of the winding is used, the other winding should be kept open circuited. To avoid circulating current in the winding, in the rotor, poles are induced in accordance with the number of poles in the stator. The limitation of this method is that only two definite speed can be obtained. That means we won't get a smooth variation of speed, or we won't get a very large variation of speed. Only two speeds. One speed is 1455, another speed is equal to 970 rpm. That is the main drawback by using two different windings, right? Or by changing number of poles. Speed variation by using by consequent pole technique method. So here observe the slide. There are two windings are there. An alternative method is to use only one winding. In the first case, we are using two separate windings. The cost increases, cost of the motor increases, and each and every time if you want to one speed to open circuit another winding, there is some complexity in that, right? Suppose when only one winding if you use, some complexity decreases, right, and cost also decreases. In this method, we will use only one winding, wound for a particular number of poles. It is possible to have one or two speeds. One double of the other, which is generally obtained by changing the connections, simply by changing the connections of the motor, stator winding then we can achieve two speeds, double speeds. Suppose one is a 500 rpm, then we'll do 1000 rpm, it is 750, or it is double to 1500 rpm. Like this, simply by changing the connections in the connections of the windings, we can achieve two different speeds, right? Let us consider a single phase of a certain winding having three taps, two terminals. That is, third terminal is left free. The distribution of the current as shown in the first figure A, right? The conductors which carry current in upward direction from south pole, while the conductor which carry current in a downward direction from north pole. So it will be observed that the connections of figure A is an 8-pole winding. Now, if these two terminals are joined together, T1 plus T2, and supply is given to T1 plus T2 and T3. So, about the first diagram, we have T1, T2 and T3. Right? Suppose if T1, T2 are joined together, right? From figure A, if you observe the direction of the current, right? So in the south pole in upward direction, in north pole in downward direction. Here the third terminal T3 is a one terminal, single terminal is open, and only supply is given to T1 and T2. By giving a supply T1 and T2, what happens? And you can observe we have a sequence of south and north poles, That means, so then we can get 8-pole machine. Suppose if T1 plus T2 is joined together, and by giving the supply T1 plus T2 and T3, then it is converted into 4-pole machine. Then the speed will be double. So this method is known as consequent pole method. With a combination of the about two methods of having two separate windings on the stator, or by serial parallel connections of the coils across the supply, but distinct speeds can be obtained. However, the smooth variation of the speed over a winder is not possible, right? Whether it is two separate windings or a single winding, by changing the number of poles in the stator winding, we won't get any two speed variations only. We'll get two speed variations, right? That is 8-pole and 4-pole, right? So this is the speed control of 3-phase induction motor. This is also from stator side. So we completed 3 methods of speed controls from stator side, that is by changing the supply voltage, by changing the supply frequency, and by changing the number of poles. By changing the supply voltage, we get a very small variation of speed variation with a large change in the supply voltage. And second one is the frequency control method. In that case also there is a one drawback. that is change in frequency, only frequency and saturation of the area flux occurs. To avoid this, we use a electronic device to control frequency and voltage. That's why we use that method is known as V by F control method, frequency control method only, but it is called V by F control method, voltage and frequency control method. By changing the number of poles, we get only two speeds, specific two speeds. Only we get two speeds only. We won't get a very smooth variation in the speed control, right? So this is from stator side, and next one is from rotor side. From rotor side, by changing the by rotor rheostat control method, by injecting the EMF in the rotor circuit, and third one is by cascade connection, right? By rotor rheostat control method, by injecting the EMF in the rotor circuit, and third one is by cascade connection, we can control the speed of a three-phase induction motor. Speed variation by rotor rheostat control method. The method is applicable to the slip ring induction motor only when external resistance is put in series with the phase of the rotor circuit, from the rotor circuit, and the rotor copper loss increases, and the slip is given by the equation slip is equal to rotor copper loss by rotor input, rotor copper loss by So when external resistance is connected in series with the rotor circuit, what happens? Automatically when resistance increases, losses increases. When losses are increases, what happens? Slip increases. If the rotor input remains constant and the increase in rotor resistance will increase the slip, So thus the motor speed NR is equal to 1 minus S into Ns will decrease. We know that when slip increases, speed decreases, rotor speed decreases. The speed below the normal only we can have. So we can have, right? Very important point is in the rheostat control method, by inserting the resistance in the rotor circuit, we can get below rated speed only. By inserting the rotor circuit resistance, what happens? Rotor copper losses increases. When rotor copper losses increases, automatically by making rotor input constant, slip increases. When slip increases, automatically speed decreases. We know that slip and speeds are inversely proportional. The main disadvantage of this method is that with increase in rotor resistance, the rotor copper losses also increases, so which decreases the efficiency of the motor. In fact, the loss is directly proportional. Right, so very good point. By using this method, losses increase. When losses increases, automatically efficiency decreases. Right. So that's why, suppose we need only for a short duration of speed variation. In that case, we will use the rheostat control method for slip ring induction motor. This is the first method from rotor side, and that too for slip ring induction motor, right? Simply by inserting the resistance in the rotor circuit, losses increases. When the losses increases, automatically slip increases. When slip increases, speed decreases, right? And second method from the rotor side in a slip ring induction motor is given by speed variation by injecting EMF in the rotor circuit. Speed variation by injecting EMF in the rotor circuit. In this method, the speed of an induction motor is varied. The speed of induction motor is varied by injecting a voltage of slip frequency. You have to inject the voltage of a slip frequency into the rotor circuit through a slip ring. Right? In the first case, we inserted a resistance, only simply resistance. In this case, we have to insert a voltage through frequency, rotor induced EMF frequency. Injected EMF frequency must be equal to rotor induced EMF frequency. Induced EMF frequency is different from injected EMF. Right? Since the speed of an induction motor depends on the total EMF acting in the rotor circuit. If the rotor is short circuit in the usual way, this EMF is induced EMF and the motor runs at a normal speed. If an EMF of the correct frequency from some other source is injected into the rotor circuit, then if the injected EMF has a component indirect opposition to the induced EMF, then the net EMF in the rotor circuit decreases, and speed will be below the normal. Then speed decreases, then we get below normal speed, right? You have to decrease. In the previous case, we have increased the resistance of the circuit. In this case, we have to decrease the EMF of the rotor circuit. By decreasing the EMF, speed also decreases, right? The speed or rotation depends upon the induced EMF, right? You have to inject the EMF by using some other source in such a way that its a component will decrease the total effective value of the effective EMF in the rotor. On the other hand, if the injected EMF has a component in phase with the induced EMF, the total EMF has a component in phase with the induced EMF, then the total EMF acting in the rotor will be increased and the speed will be above normal speed. So very important point, by using rheostat control method, so we can get only speeds below the rated speed or normal speed. But by using injected method, depends upon injected voltage. If the injected voltage component is opposite to the induced EMF, opposite to the rotor EMF, then speed decreases, we can below rated speed, right? Suppose the injected voltage is added to the rotor EMF, then the speed increases above the rated speed or above normal, right? Such injection of EMF in the rotor circuit is possible with the help of a scarge motor. We can induce EMF in the rotor circuit, right? Or by brush shifting motor. Is another important point. So how to inject EMF in the rotor circuit? By a scarge motor or by brush shifting motor. Nowadays these motors are rarely used because of the bulky construction and prohibitive cost, but in this method any speed within the working range can be obtained. But advantage is we can get any speed below rated uh, rotor injected EMF method. By injecting the EMF, speed variation by injecting EMF in the rotor circuit, right? So from the rotor side, there are two methods are there. One is uh, inserting a rotor circuit in the circuit, and another one is by injecting EMF in the rotor circuit. Injecting EMF in the rotor circuit, right? And third one is the speed variation by cascade connection. The speed variation by cascade connection. Actually, it comes under rotor resistance, rotor side only, but controlling a slip ring motor. By controlling a slip ring motor, right? We can control a slip ring motor or a squirrel cage. Sorry, we can control a squirrel cage motor or a slip ring motor by using rotor circuit. By using again the rotor circuit only, right? The EMF in the rotor circuit only. So that's why it is comes under rotor side, right? So that is the speed variation by cascade connection. Speed variation by cascade connection. Please remember, so very important method, right? In this method, so very important point, two motors are required. In this method, two motors are required, at least one of which must have a wound rotor, slip ring rotor, one of which must have a wound motor, right? It's a very important point for competitive examination. In a cascade connection, at least one motor are geared together, mechanically coupled, some geared together by decreasing the speed, geared together to drive a common load, right? So these two motors drives a common load. So three load, and these two motors are mechanically connected, right? If the stator winding of one of them, say the wound rotor motor, is connected to three-phase supply, first one, motor 1 and motor 2, you can observe in the slide, motor 1 and motor 2. So motor 1 is a slip ring type and wound type. So to this, and three-phase supply is given. Three-phase supply is connected to three-phase supply source, and its rotor winding is connected to the stator winding of the second motor, right? You can observe, first one is a wound type, the slip ring type. That means the output of the three slip rings is connected to the input of the second motor, So you can observe in the diagram, input of the second motor. The speed of the combination will be determined by the sum or difference of the numbers of the poles. Suppose if it is a 8-pole machine and it is a 6-pole machine, 8 plus 6 or 8 minus 6, which determine the speed of the combined load. P1 minus right. In practice, it is customary to connect the rotor output of the first motor to the stator of the second motor, in such a way that the rotation of the both the machines in the same direction. The rotation of the both the machine must be in the same direction, right? Under this condition, the resulting synchronous speed will be determined by by following expression. So we have one expression. By using that expression, we can determine by the speed, a synchronous speed of the combined expression, right? So very important thing, in a cascade connection, two motors are required. One motor must be wound type, another may be a wound type or squirrel type, right? And first one, and these two are mechanically coupled or through gear it is connected. And the second point is first motor is given by three-phase supply, and the first motor output, here output means the at the slip ring side, rotor side, three slip rings are connected to the input to the second motor, right? Output of the first motor, rotor output, is connected to the input to the other motor. So whatever EMF induced in the first motor, right, is the voltage source to the second motor, voltage source to the second motor, voltage source to the second motor, right? So let us consider and F1 is the supply frequency, F1 is the supply frequency, and combined synchronous speed is given, Ns is equal 120 into F1 by P1 plus P2, P1 plus P2. Further speed control it is desired can be obtained by having a second motor also if wound rotor type, and the interesting control inserting a control resistance in the rotor circuit of second motor. Thus, the combination can be made to run in the three speeds. By resistance, by inserting resistance, we can get some speed, and by number of P1 and P2 number of poles, we can get another 2 poles, another 2 speeds. So, therefore, 3 speeds can be obtained. 3 speeds can be by suppose if the second one is a slip ring type, if it is a squirrel cage type, only 2 speeds, right? So, thus the combination can be made to run in the 3 speeds. First one, the motor one may be the motor one be run separately from the mains, then Ns is equal 120 into F1 by P1. Suppose the motor 2 may be run separately from the mains, N is equal to 120 F by P2. The combination can be connected in cascade, that is equal 120 into F1 by P1 plus P2. Right, synchronous speed of first machine is given by 120 into F1 by P1. Second machine synchronous speed is equal 120 into F1 by P2. The combination may be connected to in cascade, that is equal 120 into F by P1 plus P2. P1 plus P2. Here it must first be brought up to speed either by auxiliary motor or by we know that when they are mechanically coupled, that means they must rotate with the same speed. They equate these two speeds, synchronous speed. So 120 into F1 by P1 into 1 minus S1 is equal 120 into F2 into P2 by 1 minus S2. So equate the two speeds, speed of the first motor and speed of the second motor. Why we have to equate? Why? Because they are mechanically coupled. Mechanically coupled means they must rotate with the same speed. So by using that logic, I am equating the equations. 120 into F1 into P1 by 1 minus S1, 120 into F into P2 by 1 minus S2. Right? And here by substituting F2 is equal to S1 into F1. F2 is equal to S1 times of F1. Very clear? Second motor frequency is given by the EMF in the first motor circuit, rotor circuit. The EMF in the rotor circuit is given by S times of or S1 times of supply frequency F1, where F1 is the supply frequency and F2 is the second motor frequency. So from this by cross multiplication and simplification, 120 into F and 120 into 120 cancel out, right? And I will write F2 is replaced by S1 into F1 and F1 also cancel out. Then 1 minus S1 by P1 is equal 1 minus S2 1 minus S2 into S1 by P2, right? By multiplication S1 minus S2 by P2. Then rearrangement will get 1 minus S1 by P1, that is equal S1 minus We can neglect x1 and s2. Why? Because slip is very small, s1 and s2 is very small, so you have to neglect. So the equation is 1 minus s1 by p1, that is equal s1 by p2, s1 by p2, right? Very clear. We know that what is slip? Slip s1 is equal to p2 by p1 into 1 minus s1, right? That is equal to s1 into 1 plus p2 by p1, that is equal to p2 by p1. So therefore, by simply the manipulations, then we get slip s1 is equal to p2 by p1 plus p2, p1 by p2 by p1 plus p2. That means in a cascade connection, the synchronous speed of the set is given by 120 into f1 by p1 into 1 minus s1. 1 minus s1. So 120 into f1 by p1 into 1 minus, what is s1? That is p2 by p1 plus p2. p2 by p1 plus, by simplification, then we get 120 into f1 by p1 plus p2. The set synchronous speed is given by 120 into f1 by p1 plus p2, right? p1 plus p2. So suppose p1 is 4 and p2 is equal to 2, then p1 plus p2 is 6, right? p1 plus 2 is equal to 6. That means speed is different, so number of poles changes, then automatically speed changes, right? And by simplification we can get the another speed also, that is 120 into f1 by p1 minus p2, p1 minus p2 also, p1 minus p2. That simply by changing two different number of poles of motors, then 120 into f by p1 minus p2 is a one speed, 120 f1 by p1 plus p2 is another speed. So in this method also, the actual speed will be less than the speed by slip motor. Why? Because here initially it is a 4 pole. Separate, if it is a 4 pole machine, what happens? Speed is some speed. When it increases to 6 speed decreases. Right? So this is a very important method, that is a cascade method. So very important. You have to remember only one important thing. It requires two motors. One motor is a wound type, another motor may be a squirrel cage or slip ring. And by using this method we get two speeds. So it depends upon number of poles, right? And third important point is never consider same number of poles. P1 must be different from P2. First motor poles, number of poles must be different from second pole. Never be P1 is equal to P2. P1 is equal to P2. Right? That is another important point. So the bus set, by cascading of the two motors, then we can get two speeds. One is 120 into f1 by p1 plus p2, or 120 into f1 by p1 minus p2. Two speeds can be obtained by using this cascade method. So this is also comes under rotor side, right? So summary, today we will discuss stator side. There is three methods are there. There is a number of, by changing the voltage, and by changing the supply frequency, by changing the number of poles. Again, the number of poles, we have two methods. One is the consequent winding method, and first one by simply it is designed for two windings. And from the rotor side, we have two methods. Three methods are there. One is by changing the resistance, second by injecting the EMF, and third one is a cascade method. In case of resistance, by inserting the resistance, what happens? Rotor losses increase. When losses increases, slip increases. When slip increases, speed decreases. Here you have to remember. So that means by rheostatic control method we get only below the rated speed. Then second one is EMF injected method. Again we have by injecting the voltage in such a way that suppose it opposes the induced EMF, it decreases the induced EMF in the rotor circuit, right? Then we can get below rated speed. Suppose the induced EMF is in such a way that it adds to the induced EMF. Injected voltage adds to the induced EMF, rotor EMF, then speed increases. So that's why so we can easily get rated speeds above normal speed and below normal speed. And last one is cascade method, but the main disadvantage, it requires two motors, but we get two different types of speeds, that is 120 into F1 by P1 plus P2, 120 F1 by P1 minus P2, P1 minus P2. Suppose if the second motor also so thank you very much, have a nice day.